Okay, enough with approximating the area. Let's go ahead and figure out the calculus. How are we going to actually compute the value of a definite integral, which is also the same thing as that area bounded by the function and the x-axis? Okay, so we're going to kind of extend this idea of Riemann sum. Remember, we could take these regions, and if they happen to be perfectly geometric, I could find their area by using geometry. That's what the first homework worksheet was over. Or if I have a weirdly shaped region that is not geometric, I can break it down into subintervals, and then within each subintervals, I can do a geometric shape, namely a rectangle or a trapezoid. And then if I were to add all those rectangles or all those trapezoids areas together, that will give me an approximation for that weirdly shaped region's area. That's called a Riemann sum. But we don't want an approximation anymore, and we're going to want to actually figure out the exact, not an estimation. We want an exact area for these weirdly shaped regions. And so here's kind of conceptually what's happening. Kind of like let's extend the Riemann sum. I have this interval from A to B. A is the left side, B is the right side. We're still going to split it up, but now these rectangles, obviously the more rectangles you have, the narrower each one is, and the better your approximation would be. I think we talked about that a little bit last time. The more rectangles you have, the better your approximation is going to be. The better your estimated area will be close to that exact area. So here I have just a really thin rectangle. That rectangle, I just chose it at an arbitrary x value, but we'd have this very narrow rectangle all the way on the left, and then we'd take the rectangle right next to that, then the rectangle right next to that, right? And we take all these little momentary rectangles, right? And as you get more and more and more rectangles, each one is going to get smaller and smaller and smaller, narrower. So here I just have one arbitrary rectangle kind of blown up and drawn a little bit bigger. Okay, so I just pick some x value, call it c of k, and then that rectangle at that point has a width. We'll call the width delta x. Again, the more rectangles you have, the smaller that delta x should be. So if you have 20 rectangles, that width delta x would be dependent on the 20. Or if you have 200 rectangles, right, that delta x would be dependent on the 200. K is really the number of rectangles. And then the bigger that is, the smaller each width is. But I have just that one little rectangle drawn. It has a width, delta x, and it has a height. And to find the height, you would take the x value, c of k, and I would plug it into your function, right? So the y value, the height, is your height, the y value. Okay, so I've got this area of that one rectangle. Now what I'd want to do is add all of those little areas of all of those little rectangles together. So let's kind of look through and develop the notation for a definite integral. I know the area of that one arbitrary rectangle would be base times height, or the height times base. So I have the function value times the width of the rectangle. I wouldn't just want one rectangle's areas. Riemann sum told me I would actually want all of the areas of all of the rectangles. So I'm going to add them together, and we're going to indicate that with a summation. Right, so we're going to start the sigma summation with k equals 1. That would be your first rectangle over here on the left side. And then we would move to k equals 2. That would be the next one. Then k equals 3, so on and so forth. That k is the index. So we're going to move from one region, from one rectangle to the next, starting with the first one all the way over here to this nth one, the last one. We're going to add all of those areas of all of those rectangles together, and that's a Riemann sum. Now remember, the sigma means add. That tells you where to start, 1. That tells you where to end, n. So the last one would be the nth rectangle. And then what we're adding is the area. We have the height of each rectangle times the width of each rectangle. So adding areas of rectangles together, right? That's your Riemann sum. How we make that no longer an approximation, but how we instead get an exact, precise answer is we want infinitely many rectangles. So we are going to, that's called your Riemann sum. Sorry, I forgot that line was there. But to turn the Riemann sum, the approximation, into the exact area for that definite integral, we're going to have to take a limit, right? How are we going to get that exact curve? We're going to have to take a limit. And really, you could do two different things. You could take the limit as n goes towards infinity, which means infinitely many rectangles, right? And as the n gets big, the width for each rectangle gets small. So if you take the limit as n goes to infinity, that'll mean the width of each one is going to get really, 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 really close to 0. Or you could do kind of the opposite. You could take the limit as delta x of k as the width of each rectangle goes to 0. Then as you make those narrowers smaller and smaller and smaller, as you make those rectangles narrower, then the number of rectangles is going to have to grow in order to still cover that interval from the left to the right. Typically, you think about it like this, right? Infinitely many rectangles. That's how we can turn the Riemann sum approximation into the exact area of that weirdly shaped graph, right? So now let's apply that limit. Here we could really do two different things. We have the limit as n goes towards infinity, so that means adding together infinitely many rectangles, and then each rectangle has a height, and each rectangle has a width. So let's kind of look at this notation. Remember, f of c of k, that's the y value, that's the height of the rectangle. The delta x of k, that's just the width. So right here, that's the area of one rectangle. Then you're going to add them all together, starting with the first one, going to the last one. But then you're going to take the limit as n goes to infinity. That means we're adding together infinitely many rectangles, and then all those areas of those rectangles. And that's how we're going to go through and get the definite integral notation. Now let's look at how everything translates, right? The differential dx, what does it compare to? Well, it is the equivalent of that delta x. Remember, delta x is the change in x. It's more of a geometric notation. As that limit goes towards infinity, as you get more and more and more rectangles, the width of each one gets really, really, really close to 0. But notation-wise, the delta x is like the geometry, the approximation. As that delta x gets really close to 0, the calculus notation is the dx. But that's what translates. And then the height of the rectangle, f of c of k, that's just the height of your function, right? F of x. And then we have the rest of it. We have this limit as n goes to infinity of the summation starting with k equals 1 all the way to k equals n. That's what the integration symbol begins. That's what the integration symbol represents. Right. So the reason why it looks kind of like a squiggly looking S is because it stands for a summation, right? Summation starts with an S, so it kind of makes sense that that integration also looks like an S. This integration means I'm adding together infinitely many things. What am I adding together? Area. There's the height of the rectangle, there's the width of the rectangle, but that's just really, really, really close to 0, and that's just your y value from your function. Right, so everything for this derivative notation, or this integral notation, is there for a reason. Why do I have a dx? Why, when you do an integration, does that dx have to be there? Well, if it wasn't there, think about what you're doing. You'd be adding together infinitely many things, but if the dx isn't there, all you're doing is adding together f of x. You're adding together heights of a rectangle. Or if you add a bunch of heights, height is just one-dimensional, right? It's just like a line. If you were adding together heights, you wouldn't get an area. You have to add together area to get that total area. So if that dx wasn't there, that means this delta x wouldn't be there. You're just adding together the y values. You're adding together the heights of the rectangles. That's not how you get the area bounded by the curve. If you want the area, break it down. You have a rectangle. Each rectangle has a height, and each rectangle has a width. So why is that dx there? Because we're adding together infinitely many areas of infinitely many rectangles, and each area of each rectangle has a height and has a width, right? So we're adding together infinitely many things. There's the function. That's what you need to integrate. It's the y values. That's going to be how you accumulate all your distance, and then that's the little widths. Those really, really, really narrow rectangles. They get really close to 0. But yeah, that's why that dx is there. It's the width of all those infinitely small rectangles. And then you could take the limit as delta x goes to 0. It's going to accomplish the same thing. If the width of each rectangle goes to 0, then that's going to mandate that, hey, there's going to have to be more and more and more rectangles, right? There's going to need to be infinitely many of them in order to bridge that gap and to go all the way from the left side to the right. Okay, so this integral notation, hopefully it makes sense. Again, I wouldn't really stress a whole lot about that one. I think this one is the one that makes a little bit more logical sense. We're adding together a bunch of areas. That's the height of each rectangle. That's the width of each rectangle, right? So that's one rectangle. That's a Riemann sum, adding them together, starting with the first one, going to the last one. But how we make the area exact is I need infinitely many rectangles. But people just got tired of writing limit. N goes to infinity, summation, starting with the first, going to the nth. People got tired of writing that. So they created this new notation. It's called the integral symbol. This, kind of like k equals 1, this is going to tell me the lower limit. Where am I going to begin my summation? Where am I going to begin to accumulate area? And then that b, that's the upper value, kind of like the n. that's going to be where on this graph do I stop accumulating area, right? So instead of writing limit as n goes to infinity of the summation, instead of having all this, we created, not we, I didn't do anything with it, but the people in the past who kind of developed the calculus notation, like Newton, they created this integration symbol to represent an infinite summation. Okay, so that's a lot of cool story. Well, let's actually figure out how to do it, right? Enough of this stuff. Let's figure out how to do it. Let's look. If the function is positive, then the area bounded by that function and the x-axis is given by this integral, like we know. All right, let's see this note at the bottom. See what it says. Remember, a definite integral is a Riemann sum as the number of rectangle goes to infinity, and therefore the area bounded by the curve becomes exact. It's not just an approximation. The more rectangles you have, the better. So if I have infinitely many rectangles, you would actually get the correct, precise, exact area bounded by that graph. Even if it's a weirdly shaped region, you're going to get the exact area. Okay, but we're not going to actually have to do a limit process. How we calculate these integrals is actually very simple. Okay, let's go through and let's try to see this fundamental theorem of calculus. It's called the first FTC. How we do a definite integral, and we're going to work more with this in a little bit. We're just going to kind of introduce ourselves to it today. Let's try to see if we can connect the dots ourselves. The other day we did geometry to find answers to this, right? This function x plus 1, it's linear. It's shifted 1, and it's got a slope of 1. So I could sketch this function, and then the area between 2 and 4, so 1, 2, 3, 4. If I were to find, ooh, that's 1, isn't it? It needs to be at 2. Here we go. 2 to 4. If I wanted to find the area of this region, if it's perfectly geometric, you don't have to use calculus. You're welcome to use geometry if the graph is geometric. But we're going to also learn that the calculus isn't too bad. But if it's geometric, you can use geometry. Let's go for it. That's a trapezoid. So we know the area of the trapezoid is 1/2, and then the width is 4 minus 2. So the width of that trapezoid is 2. And then I need the base 1. And then the base 2, add them together. So if you plug in 2 into the function, you're going to get 3. So this height is 3. And then if you plug in 4 into the function, this height right here is 5. So that's 5. That's 3. And then obviously the width is 2. So finding the area using geometry, that's 8. Those are going to cancel. I know the value for that definite integral is going to be 8. And what's nice is that the calculator can always check. Calculators cannot do an indefinite integral because the answer to an indefinite integral is a function. However, the answer to a definite integral is a number. And if you do Math 9, the calculator can do definite integrals for you. So let's just check it. Yeah, look at that, 8. We can do geometry. Hooray! Okay, so we know what that integral is. It's got to be 8. Now let's see if we can kind of connect it to our indefinite integral skills. I know how to undo a derivative, right? I add 1 to the exponent, divide by the new number. So the integration of x would be 1/2 x squared. And I know the integration of 1 would just be x. And what's going to be kind of nice is that for definite integrals, you're not going to need to worry about the plus c. Okay, we'll kind of explain why in just a minute. But for an indefinite integral, yes, your answer would be this function, that antiderivative function, and you would be very concerned with the plus c. Okay, well, let's see if I can kind of connect this antiderivative function with the x values. Remember, we used 2 and 4. Let's see if we could connect this function, x equals 2, x equals 4, and let's see if we could come up with that 8. All right, so let's plug in that lower limit for the integral, right? Indefinite means there's no numbers. That means you don't have to evaluate it. You just undo the derivative, put the plus c, and you call it a day. But if it's a definite integral, that means evaluate it. Let's see what happens. If I plug in 2 into this integrated function, let's see, it would be 1/2 2 squared plus 2. I'm going to leave off the plus c for now, but we'll come back and talk about it. That would be 4. 4 divided by 2 is 2. 2 plus 2 is 4. Okay, so that's 4. If you plug in 2, you get out 4. Now, if I plug in 4, let's see, we'd have 1/2 4 squared plus 4. So that's 16. 16 divided by 2 would be 8. 8 plus 4 would be 12. So I know I can integrate, and I know I can evaluate, which just means plug it in. Let's see, what could I do with these two numbers? If I have 12, which came from plugging in the upper limit for my integral, it's the upper evaluation, and if I have 4, which is the plugging in the evaluation for the lower limit, how could I potentially use the 12 and the 4 to get 8? Well, that's right. You could subtract. You could do 12 minus 4 equals 8. So if you're thinking about it, I could basically do the integration, right? I could undo the derivative, and then it tells me if I plug in the upper value, whatever number's up here, I plug that in first, and then if I take the lower evaluation, plug it in second, if I just do the subtraction, that's going to give me the area bounded by that graph, right? F of 4 minus f of 2 gave me the integration from 2 to 4 of this derivative, or of this x plus 1. Right, so you have to integrate, and then you have to evaluate, and here f would be that original function, the integrated function. Integrated function. Not this original, right? It would be the antiderivative of this. And it's always going to work out that way. How I find the area via calculus is just really 2 steps. You integrate, so I undo the derivative, and then you evaluate. And how you evaluate? You plug in the upper number first, then you subtract the plugging in of the lower number. Right, let's move it on. That's your fundamental theorem of calculus. Integrating gives you well, I guess we'll see it in the bottom. Let's try it on this next example. So if I integrate, the integration, the antiderivative of 3x squared, I know is x cubed. Now, when you integrate, remember, you're going to drop the integration symbol, and you're going to drop the differential, because remember, that's telling you to add together infinitely many rectangles. That's the height of each rectangle. There's the width of each rectangle. But notation-wise, when I integrate, that stuff drops off. For an indefinite integral, you would put plus c and you would be done. But for a definite integral, I have to plug in the 1 and I have to plug in the 2. So typically what you're going to see is this little evaluation bar. Right? So I integrate, I undo the derivative, and when you do that, the integration symbol drops off, the differential drops off, but you still need to evaluate. So that's what that little bar means, evaluation. And then how I evaluate is I plug in the upper number first, and then I subtract the lower evaluation. 2 cubed would be 8. 1 cubed is 1. 8 minus 1 is 7. So if I were to graph this function, 3x squared, which is a parabola, it's just got a vertical stretch. So it's going to look more or less like this. Let's call that y equals 3x squared. If I wanted to find the area bounded by this parabola between, let's call it 1 and 2, right? If I wanted to find it, there's 1, there's 2. If I wanted to find the area of this weirdly shaped region, it's not a trapezoid, right? Because that top would be curved. You could approximate it pretty well probably with trapezoids, or if you split it up and did multiple trapezoids, you could get really accurate. But how I can find the area of that weirdly shaped region, which is not 100% geometric, how I can find that area is calculus. And I know the area of that region is going to be 7. And 7 is not an estimate. It's not approximated. That's the exact area of that weirdly shaped region. Okay, so how I can integrate? It's pretty easy. When I see this function, right, if it starts with f prime, you're going to integrate. So you move up one step, right? If you think about this kind of ladder of functions, we have f, take the derivative f prime, take the derivative f double prime. Going down the ladder is taking a derivative. Coming back up the ladder is integrating. And remember, typically above f, you would see it denoted with a capital F. But if I'm integrating f prime, if I'm starting here, I have to undo the derivative, which means I'm going to be working at the f level. And then I would need to evaluate, which means plug in the upper number, and then subtract the plugging in of the lower number. Now, this fundamental theorem of calculus, you might hopefully think that it's a little bit important, right? It's not called the sometimes, maybe occasionally a little bit useful theorem of calculus. It's the fundamental theorem of calculus. It's kind of a big deal. It's how we do a lot of stuff with integral calculus, and it's really very easy. You integrate, undo the derivative, and then you evaluate. Plug in the upper limit, then you plug in the lower limit. That's how we go through and we accumulate all this change, all this area underneath these graphs. If you were to integrate the second derivative, it doesn't always have to start. Integrate f prime, work with f. If you were to integrate the second derivative, right, if you started here, go up one level, that's what integrate means, which I'd be at the f prime level then, a to b, and I could have f prime of b minus f prime of a, right? That would also work. That's also a perfectly good expression of the fundamental theorem of calculus. It doesn't have to always start with f prime and then end up with you plugging in at the f level. What this theorem says is that regardless of what this is, right? It could be the first derivative, it could be the fifth derivative, it could be whatever, nth derivative, or it could be f. What this theorem says is you integrate. So wherever you start, you go up one level, and then you evaluate. So if I was integrating f from a to b, you would see it denoted with the capital B minus the capital F of a. You always integrate, so you go up one level, and then you evaluate by plugging in the upper limit, and then you subtract the plugging in of the lower limit. Most of the time, though, you're going to see it written as integrate f prime to evaluate with f, but it doesn't have to be. If you integrated the 50th derivative, then you would be plugging in with the 49th derivative, right? Or if I was integrating the 100th derivative, you would be plugging in to the 99th derivative. You undo the derivative, you integrate, and then you evaluate, plug in the upper number, plug in the lower number. Okay, let us go through and do some examples. Okay, so let's look at this first one. It says the integration of x squared plus 3, and we're going to accumulate all the area. That's a parabola shifted up 3 units. I'm going to get the area bounded by that weirdly shaped graph between 1 and 2. It's going to be easy. Integrate, and then evaluate. First thing, let's integrate. Add 1 to the exponent, divide by that new number. The integration of 3 with respect to x would be 3x. Ooh, I didn't talk about something. Let me go back. This just came into my brain. I didn't mention this, but let's look at it. Why is the plus c not important? Well, if you had put it there, let's see, then this would have had a plus c, and then this would have had a plus c, so then you would have had 4 plus c, you would have had 12 plus c. Look what would happen. If you took 12 plus c minus 4 plus c, distribute the negative, you'd have minus 4 minus c. The c's would end up canceling. Or here, if you put a plus c, you'd have plus c, but then when you have 2x plus c in parentheses, then when you distribute that negative, the c's would cancel. You do not need to put a plus c when you have a definite integral. If you do, it should cancel. But since it cancels, it's really not proper to even put it, right? You need the plus c when you do an indefinite integral, when you're trying to find that antiderivative function, because, hey, that c represents the constant that could have been there on my original function, but then went away when I took the derivative. For a definite integral, though, you do not need it, right? You do not need, please don't put the plus c for your definite integrals. If it's there, it should cancel, but since it's going to cancel, please just don't put it, right? It's not proper, don't put it there. But that's why you don't need the plus c. Yeah, I kind of forgot. And then this example kind of made me think of it. Okay, so let us finish. We integrated. Now I still need to evaluate. So that little bar is the evaluation bar. Remember, when you integrate, that integration symbol should drop off. That differential should drop off. If it was an indefinite integral, I would swap that notation with the plus c, and then I would be done. Since it's a definite integral, when that notation drops, I'm going to pick up the evaluation bar. Okay, but I don't need to add together infinitely many rectangles. I've already done that. So once you do the calculus, that symbol should drop. It's like when you do the square root of 25, right, and you get 5. The square root symbol is not there anymore. You don't leave the answer as root of 5. No, when you apply the mathematical procedure of taking the square root, you don't write that symbol again, right? Once you've done it, you don't write that same symbol. Or if you had something like 4 squared, when it's 16, the square root isn't there. Like once you do the operation, that symbol drops off. Once you integrate, that symbol should drop off. It really annoys me when I see people still have it. No, that just shows you really have no idea what you're doing. When you integrate, that drops off, that drops off. If it's an indefinite integral, you would pick up a plus c, and then you would be done. We love indefinite integrals. As long as you put your plus c, they're much faster. But if it's a definite integral, when you integrate, that stuff drops off, but you pick up this evaluation bar, which means I have to plug in 2, plug in 1, and then subtract. All right, let's plug in 2. 1/3, 2 to the 3rd power, and then plus 3 times 2. There's your upper evaluation. Minus, please put your parentheses. If you don't put your parentheses, you're likely to make some mistakes. Plus 3 times 1. So I have the upper evaluation, plugging in the upper number first. Then I'm going to subtract the lower evaluation. Here we go, 8/3 plus 6. Distribute the negative. That's all going to be 1/3. So minus 1/3, minus 3. Let's combine some stuff. We have an 8/3 and a negative 1/3. So that's going to be 7/3. 6 minus 3 would be 3. You could leave the answer like this. On an AP exam, that would be fine. That is numerically equivalent to the next thing, which I'm going to write. But on your AP exams, you do not need to combine things that don't have the same denominator. If it was a free response. Okay, if it was a multiple choice question, I'd guarantee you the answer wouldn't look like that. But if it was a free response, that would be an okay place to stop. You don't have to combine stuff with different denominators. If you've got terms that are over 3, combine the over 3s. If you've got whole numbers, combine the whole numbers. But if it's a free response, you don't have to combine the stuff that have different denominators. Wait for Elias to get back. If I did want to combine these, what I would need to do is change this to 9/3, right? I need to get a common denominator, and then I can add them together, and I could get this singular answer at the end as 16/3. Okay, so it's not too bad, but just know, like doing this extra couple of steps, combining the fractions, it's just opportunity to make a mistake. If you want to do it, make sure you do it correctly, but you do not have to. It's perfectly okay to stop here. Yeah, that's how you do a definite integral. Integrate, and then evaluate. Let's do probably 1 or 2 more. Let's probably do 2 more, and then we'll end. All right, now here I've got a quotient. And remember, there is no quotient rule for integration, so what I'm going to have to do is simplify first. Okay, so I'm going to take this and I'm going to split it up. I'm going to have the integration from 1 to 9 still, but I'm going to split it up. I have x over the root of x, so that's an x to the first. That's an x to the 1/2 on the bottom. So that would reduce. You have an x to the 1/2 left over on the top. Then you have a minus 4 over the root of x. That's going to be minus 4x to the negative 1/2 power. So algebraically, I've just rewritten it so that it's no longer a quotient, right? And now I can go through and I can integrate. Add 1 to the exponent, divide by that new number, so it's going to kick out the reciprocal. Add 1 to this exponent, it's going to be a positive 1/2. Divide by that new number, so that's going to kick out a 2. Minus 4 times 2, minus 8. So there's the integration. Remember, if this was an indefinite, you would put plus c, and then you would be done. Since it's a definite, I have to plug in the 9 and then plug in the 1. Ooh, I'm off the screen, sorry. So I integrated, and then if it was an indefinite, plus c, and you'd be done. Since it's definite, you need the evaluation bar lower and then the upper. And remember, plug in the upper one first. Okay, so let's go for it. We got 2/3. 9 to the 3/2 power, minus 8 times 9 to the 1/2 power, and then your lower evaluation plugging in 1. Okay, so we integrate, that's all the calculus, and then we evaluate, a lot of arithmetic. Okay, let's plug this in and let's get this answer. Let's see, 9 to the 3/2 power. You can do 9 cubed, and then try to take the square root of that big number, or you can do 9 to the 1/2 power. You can take the root first, and then take the cube of that smaller number. It's always easier when you have a rational exponent. It's always easier to do the root, the bottom power first, because that's going to keep the number smaller. All right, so let's look at this. 9, if you square root it, would give you 3. And then 3 to the third power is 27. So here, this is all 27. And 27 times 2 would give me 54 thirds. 9 to the 1/2 power is 3. 8 times 3 would be 24. 1 to the any power is 1. So that's all 1. That's all 1. That's great. Distribute your negative, though. So minus 2/3 minus negative plus 8. Again, when you have a question like this, combine your over 3's, combine your whole numbers. You wouldn't necessarily need to go farther than that, though. Okay, let us see. 54 divided by 3 also, I think that works pretty well. I think that's 18. Let's check. 54 divided by 3. Yeah, there we go. So you could put it as 54 thirds, or if you wanted to combine it, I'm just gonna reduce it to 18. All right, so let's combine the whole numbers. So let's see, I've got a 26 minus 24. So that's whole number is going to combine and be a 2, and then minus 2/3. So that is a perfectly good way of leaving your answer. By the way, if you had left it as the 54 thirds, let's see what we would have gotten. You would have combined those, so you would have had a 52 thirds, and then you would have had a minus 16. That would also be an equally valid answer. So like some of these ones may look different. Let's check though. If I did 2 minus 2/3, then if I did 52 thirds minus 16, look at that. They are the same thing. Sam, do you need to go? So either one of those would be fine. Even though they look different, they're mathematically equivalent. So they would both be fine. Those are safe stopping places. Remember, if you have over 3's, combine them. If you have whole numbers, combine them. There's different ways this answer could look. If we all simplify it, right? So if you change this to 6 thirds, 6 over 3, 6 minus 2 would be 4 thirds. Or if you were to change this, multiply it by 3, that would be 48 over 3. 52 minus 48 would also give you the 4 thirds. So if you were to simplify it and get it down to one fraction, everyone would get to this same answer. But if you wanted to stop earlier, it's okay. Your answer may look slightly different. But remember, this is a definite integral. If there's ever any uncertainty, just check it. Let's do math 9. And we can do the integration from 1 to 9. You're typing in what the original function was. So here we go. X minus 4, make sure it's in parentheses, divided by square root of x with respect to x. And you're going to end up getting that number, which let's see if it changed it into a fraction for us. Yep, 4 thirds. So we can always use math 9 to check, right? I know on your homework you could make it really quick by just doing math 9 on everything. I would strongly suggest that you don't do that. You guys need practice with the arithmetic. The calculus is fairly easy, integrating. It's all, the mistakes are going to happen here. The mistakes happen with the arithmetic, like dropping a negative or just adding numbers incorrectly. You guys could probably use the practice with the arithmetic. So while the calculator could get you the answer, I would strongly suggest that you practice, because sometimes on the AP exam you have entire non-calculator sections and you need to be able to do stuff like this by hand. So don't become too dependent on having the calculator to do it for you. All right, let's do one more and then we'll end this video. Here we go, last one, secant squared, and we're going to integrate it from 0 to pi over 4. First thing you got to do is integrate, right? Undo the derivative. And the integration of secant squared is tangent. If it was indefinite, I would put plus c. Since it's definite, I need to evaluate. So that means I'm going to plug in the upper one first. So I have tangent of pi over 4 minus tangent of 0. So then we need to go to our unit circle and figure out, okay, what is the tangent of pi over 4? Well, pi over 4 is right here, where it's root 2 over 2, root 2 over 2, so y over x. The tangent of pi over 4 is actually really nice. It's 1. And here's 0. It's the point, 1, 0. Y over x, 0 divided by 1, that's 0. So I don't really like seeing tangents, but if I see a tangent, I'm going to hope that it's a whole number of pi, or I'm going to hope that it's an over 4 angle, because those over 4s are either going to be positive ones or negative ones. So that ended up being 1. That was 0. 1 minus 0 is 1. There you go. your parents ask what you did in calculus today, you can either tell them, oh, 1 minus 0, or you could be more impressive and you could tell them, oh, I added together infinitely many rectangles. That's a little bit more impressive. We're going to pause and we're going to pick up with the next example, which is an absolute value function. We will do that in the next video.